Hello folks, and welcome to this lesson on buffers. By the end of this lesson, you should be able to describe the composition of buffer solutions and explain how a buffer works. So whether you've heard of buffers up until this point or not really depends on the type of life that you live, but buffers are actually present everywhere, even inside our own bodies. Now, a buffer solution itself is an aqueous solution that resists changes in pH when a small amount of acid, base, or water is added. Now, if you take a bit of water, a glass of water, and toss a little bit of acid in there, the pH is going to change depending on how much acid there is. H3O positive, hydronium ion concentration changes, etc., and so forth. Now, the thing is, with certain solutions, even if you toss in a bit of acid, depending on the solution, if it's a buffer, that solution might not change its pH as much as you expect it to, considering how much hydronium ions you've actually put into it. When that sort of thing happens, that's when you have a buffer. Now, you can have buffers at all color of the pH scale. You can have acidic buffers, you can have neutral buffers, and you can also have basic buffers as well. You can have solutions that resist changes to pH that are acidic or neutral or basic and everything in between. Now, there are several ways for how you can make a buffer, and part of the composition of buffers and what you decide to make a buffer out of will depend on what pH you need it to be. The two big ones are going to be when you have a weak acid and the salt of its conjugate base. For example, if you put ethanoic acid and sodium ethanoate together, or if you have a weak base and you take the salt of its conjugate acid, like if you were to take ammonia and ammonium chloride and put them together. Now, this case will give you an acidic buffer. This case will give you a basic one. There is a reason why I have italicized these parts of these names, but I'm not going to talk about them yet. I'm going to introduce you to a few of the other types of buffers as well. You can also make buffers using the anions of two acid salts, and you can also make a buffer using the anions of an acid salt and a normal salt as well. And honestly, depending on what you're using, you can get those different pHs that you need to get. Now, at the end of the day, no matter what it is you use to create a buffer, the way that a buffer works is going to be through Le Chatelier's principle, and it also takes advantage of how weak acids and bases work as well. Now, let's use one of those examples to talk about how buffers work to resist those pH changes. Now, here we have one example of a buffer. You have your ethanoic acid plus sodium ethanoate solution. And again, this is a weak acid, salt of the conjugate base combo. Now, whenever it comes to these buffers, no matter whether you're using a weak acid, weak base, or various different salts, the key thing is that the important bits of your buffer solution are going to be a conjugate acid-base pair. Now, whenever you have a conjugate acid-base pair, one of them is always going to be charged, whether it's a positive charge or a negative charge, depending on the pair that you have. If you remember, I always tell you that you cannot go out and get a jar of anions on their own. They'll all repel each other, and then you're left with nothing in the bottle that you have. So that's why we're working with a conjugate acid and the salt of a conjugate base. Now, the thing is that we need this bit. This bit is the important bit in this buffer, but again, it has a charge, so we're getting it as a salt. Now, when you are choosing your salt, you do want to be careful of that other ion that's going to be part of that salt. That other ion that is part of your salt cannot change the pH of this solution. If this thing is going to change the pH of your solution, you're not going to be able to make a buffer solution with the exact parameters that you need. You're going to have to deal with what is going on with that other thing. So you want to make sure that this isn't going to change the pH. So this part is the conjugate base of a weak acid. This, you want it to be the other side of a strong, in this particular case, base. So you remember the whole salts of acids and bases thing? Same sort of thing. You want to have this to be something that's going to keep your solution neutral because you want the other bit to be the one that controls anything that's going on. You want this to be not involved. That's why when in the slide before I had the sodium italicized, that comes from a strong base. And in the other one where we had our weak base and salt of the conjugate acid, you had the chloride, which was italicized. And the chloride ion comes from a strong acid. So that chloride isn't going to do anything to the pH of that particular buffer. The last thing that you need to know about is the fact that when you're making this buffer solution, you need to have considerable concentrations of each of these weak acids and conjugate bases. The having considerable quantities is a very important part for how these buffers work. So let's say you have your buffer solution, this one is acidic, it's at some acidic pH. Let's say you toss a little bit of acid in there. So when you toss a little bit of acid in there, the concentration of your hydronium ion is going to increase. Based on Le Chatelier's principle, what's going to happen is we're going to reduce the stress that has been introduced to this system in equilibrium. So the system is going to move to decrease that increased hydronium ion concentration. And to do that, the equilibrium is going to shift to the left. Now, this buffer solution is able to shift it to the left because it has enough of this particular conjugate base. So if you look at what's just happened overall, yes, you did start out by increasing the pH or increasing the hydronium ion concentration, decreasing the pH of your solution, but some of that was sort of reversed back because of Le Chatelier's principle. Now, if instead you added a bit of hydroxide to it, you try to increase that pH a bit, what will happen is that hydroxide is going to react with the hydronium ions that are there, produces water, and so you would be decreasing the hydronium ion concentration. Now, when you do that, because we have a system in equilibrium, it is going to shift to reduce the stress of that. This can shift to the right, and so you're going to be raising the hydronium ion concentration a little bit after that initial splash of hydroxide. So you did add base, and that would have lowered that hydronium ion concentration, but because of Le Chatelier's principle, you're not going to be reducing it as much as the hydroxide you originally put in. Now, one key thing to remember is that buffers won't work forever, and they are not sort of infinite, so to say. If you put in so much acid or so much base that you completely use up either one of these conjugate acid-base pairs, then it's not going to be able to buffer. If this needs to shift to the right because of Le Chatelier's, but there's none of this stuff, then it's not going to be able to shift to the right. And that's it. No more buffer. Right? And that's the end of this lesson. I'll see you next time.